Hi, I'm Charan Reddy. I'm going to talk about the problem statement of the current project.
Hi, I'm Baruz Moniri and I will be talking about this hyperparameter tuning.
Hi, I am Raj. I will explain the alternate methods.
Hi, I am Ubaid. I'm going to talk about the results.
Coming to the project, over the past several years, reinforcement learning has been proven to have a wide variety of successful applications, including robotic control. Different approaches have been proposed and implemented to solve such problems. In this project, we target to launch a lunar lander using an open API gym module with the help of reinforcement learning methods. The environment shows the position where the lander must land at a desired location with a low gravity radius. The main objective of the agent here is to land the lunar smoothly and in an efficient way. This environment has four actions and a state space of 8 with rewards ranging from minus infinity to plus infinity. A reward of landing with zero speed ranges between 100 to 140 points. Landing outside the landing pad or crash landing is minus 100 rewards, and for the correct landing we will get 100 rewards. For the smooth landing we will get 200 points, with each leg on the ground taking a reward of plus 10 extra points, followed by implementation.
Hi, yes, the implementation code involved in downloading libraries, gym library, and hyperparameters that were tested were activation functions such as leaky relu, softmax, and tan function. So the layers that were added and subtracted were dense and fully connected layers. Up to 2 layers were the maximum, and adding any more layer after 2 layers proved to be not having any beneficial effects on the results. Another hyperparameter that was tested was the learning rate and within the optimizer, which actually, if we learn any faster, we don't optimize exploration. The second Another hyperparameter was the replay buffer. The maximum replay buffer is 10,000, but the number of samples taken from the replay buffer were increased to 100 and 1000, but actually, because this is a sample, it didn't improve the results any further than 100. So a sample of between 50 and 100 were as good as taking 1000 samples, because the results were averaged. The final hyperparameter that was tested was the epsilon, which is reduced by the game by this equation here. As the game goes on, it's automatically reduced from 1. So at the beginning of the game, it's 1. We tested it to be 0.15 and 0.5, but the results were terrible to start with, and did not improve. So the exploration is high at the beginning of the game, with the epsilon of 1, and it's automatically reduced so that the exploitation rate starts to increase as the game continues. Okay, so we're going back to Raj now.
Coming to the alternative method, you can use search or Q-learning, but main problem with this method is it involves positive bias. For instance, let's take some actions whose true values are 0, but due to uncertainty, their estimated values are sometimes above 0 and sometimes below 0. Taking the maximum of these values gives a positive value, which leads to positive maximization bias. In order to overcome this maximization bias, we have to use a secondary Q table with a separate Q function, followed by results.
Okay, Obaid will talk about the results here.
Before training the model, as we could see here, we got a bad result. The maximum reward we got was 293 with epsilon 0.317. As we could see here, the red represents the double Q learning and the blue represents the single Q learning. At the beginning, the single Q learning produced better results than the double Q learning because the double Q learning has two cables to fill. But at the end, it produced a better result. The maximum reward we got with the double Q learning is 195.213, while we got 145 for the Q learning. As we could see here, that the double Q learning produced better output than single Q learning. And as we could see, the single Q learning produced a result which is lower than zero, which is in the negative side.